We have models for all sorts of aspects of our lives. For example, I know that if I take too long checking the internet in the morning, I'm going to be late to work. I have a model in my head about how the subway functions. There are times when that model will be wrong. Sometimes there are delays that I haven't anticipated. But most of the time, my model works. In that case, my model is based on simple cause and effect. Those types of models work for really simple systems, but not for complex systems like climate. Here's why. When we're talking about climate, it can be really difficult to figure out, well, which thing is the cause and which thing is the effect. With that in mind, I want to think about systems that are in equilibrium, systems that are stable. Imagine a ball sitting at the very top of a hill. That ball isn't moving because it's on a little flat bit right at the very top. So it's in equilibrium. But is it stable? Well, no, because the slightest push in one direction or another would cause it to roll uncontrollably in that direction. In contrast, imagine a ball sitting at the bottom of a valley. It's also not moving, so it's also in equilibrium. But with that ball, if you give it a little push, it'll go slightly up the side of the next hill and then roll back down to where it started. You push it the other way, the same thing will happen. It'll return to where it began. There are systems that are dominated by each of these types of equilibria. In the climate system, we mostly deal with feedbacks that are positive. What does it mean for a feedback to be positive? Well, this isn't positive in the sense of good or bad. This is positive meaning one direction. So let's go back to that first example, the ball sitting at the top of the hill. If I give it a small push to my left, it's going to keep going to my left and keep going and keep going and keep going. That's a positive feedback because it happens in one direction. The ball in the valley undergoes negative feedback. If I push it to the left, it'll go a little bit and then it'll return to the middle. So what causes a feedback to begin? Well, I said before that it was a little push in one direction. That push can also be called a forcing. We can think of the amount of sunlight we get as a forcing. That forces the system to do certain things. The system can respond in a lot of ways, but it's limited by how it's being forced. Your body is governed by a lot of negative feedback systems. Biology in general likes negative feedback because it likes to keep things nice and even. For example, if I get too hot, I'm going to start to sweat. So my system has been pushed out of its preferred location into a warmer situation. That's okay. I'll do things like sweat, and then my body will go back to the temperature it was at before. Negative feedback. By the same token, if I get too cold, I'll shiver, and my body temperature will come back up. That allows my body to stay at a comfortable temperature. Our climate system is dominated by positive feedbacks, feedbacks that take a small push and amplify it into a much larger effect. You can think about a concert going on in some huge stadium. The musician might only move their finger a tiny bit with holding a guitar pick against a guitar, but the sound is routed through preamps and amplifiers that allow it to fill an entire stadium. Our climate system does that. There are many examples, but I'm going to give you one that I think will help you understand not only forcings and feedbacks, but also a really important part of the climate system, the ice. One thing you should know about ice is that it's shiny. It reflects a lot of light. There's a term for that scientifically, which is albedo. A high albedo object, like a mirror, could have an albedo of 100%. It reflects all the light that hits it. Well, in nature, nothing's really quite that perfect, but it could have a pretty high albedo, maybe 90%. On the other end of the spectrum, you have something like open water. I know we're used to thinking about water as being blue, but when you fly over the ocean and you look down, you'll notice that it's pretty dark. That means it's absorbing most of the light that's incident on it and reflecting very little. So imagine we have this situation, an area of open water about half covered in ice. When the sunlight hits the ice, a little bit of that heat is absorbed, but most of it's reflected back. That keeps the ice nice and cool. It's also why you can get a pretty bad sunburn when you're out skiing. The open ocean, however, absorbs most of the light that it gets and only reflects a little bit. That absorbed light allows the ocean to stay, if not warm, at least warmer than freezing, so it doesn't become solid ice. And so we have a nice stable situation, ice and open water. But now imagine we introduce a forcing to that system, just a little bit of a push. An unusually cloudy winter, a cold day. It gets just a little bit colder than usual. Not a big change. Well, what's going to happen? Nothing's going to happen to the ice. Maybe it'll get a little bit colder, but it's already frozen. But think about the water. It's not getting as much heat as it previously did. That's okay. Again, only a small effect. Except now some of that water is going to freeze into ice. So there's just a little more ice than there was before, and a little less water. But now think back to the albedo. If there's a little more ice, the albedo of the entire area has increased. It's much shinier. So more light is going to be reflected and less is going to be absorbed. When that happens, it's going to get just a little bit colder. And you know what happens next? A little bit more of the water will freeze. So a little bit more of the light will be reflected and it will get a little bit colder. That's going to keep happening little bit by little bit by little bit until the whole area becomes iced over. That's how glacial stages begin. Now think about the opposite situation. It's just a little warmer than average. And again, we're starting with our half ice, half water situation. So you have an unusually hot summer, some cloudless days. A little bit of the ice just around the edges is going to melt. But now more of your area is open water and less of it is ice. And remember, open water is much better at absorbing heat than ice is. Now you have an area with just a slightly lower albedo than you had before. That means it's going to get warmer and more of the ice is going to melt. Once more of the ice melts, same thing happens. It's even less shiny, so it's going to absorb even more heat, so it's going to melt even more. And this system can also keep going until you have an ice-free surface. In both directions, it's called positive feedback, because in each example, a small push in one direction leads to a continuation of the system in that direction. Part of the reason that people like me worry about climate change is that our climate system is dominated by these positive feedbacks. It responds really violently to just very small changes. If we had a climate that was dominated by negative feedbacks, we wouldn't be as concerned about adding CO2 to the atmosphere. So it's not that we're adding so much CO2 that it will immediately become as warm as Venus or anything crazy like that. It's that our system takes these little pushes and amplifies them. And we end up with big changes.